If you are thinking, well, we always talked about if there is a read, then inodes are helping us to locate the position of that file or locate the block where that file is stored. But what if there is a write? If there is a write, the key first step that you should think of is now you need to go and find an empty space from the disk. How do you go and find an empty space on the disk? Simple enough, right? Just start looking from the beginning of the disk. As soon as you find any empty space, well, that's the place you can store the data, right? Do you want to do that? Every time there is a write request, do you want to like start searching every block right from the beginning of the disk to find if there is an empty block? You will place a part of the file that you want to write that fits into that block there, and then you would continue your quest until you find another empty block, put a part there, and then let's say you completed your quest and you were not able to fit an entire file, then you say that, hey, sorry, I tried, but I couldn't fit the file. So report that to the user. Do you think that's an efficient way to do things? No, definitely not. Well, so then that brings us to a second very important metadata that we want to maintain about our file system implementation. That is allocation structures. Or we can also call it as allocation tracking structures. What are these? These are primary structures to identify whether inode or data block are free or allocated. So now in our disk, we have, this is our cool disk. We have first 5, 6, 7. So we have this first 8 blocks reserved for metadata. The remaining is for all the data. Among these first 8 blocks, we reserve 5 blocks. So we reserve these 5 blocks to store our inodes. And whenever we have a new write request, we need to make a space to store inode for that inode structure for that file. And we also need to make a space to store the original content of that file. So we need to make some space in this one of the 5 inode blocks, as well as we need to search some empty space in this data blocks to store the file itself. So this allocation structure could say us now where do we have an available spot, or which block has some space for this new inode structure to be stored. And allocation structure could also say us now where to actually put the data in that file. So where to have the space, where do we have free space in the nodes reserved for the inode, and where do we have free space in the blocks reserved for the data blocks. Let's say for this allocation structures, we reserve 2 blocks. One for inodes and one for data blocks. Now, what are the different ways in which we could maintain these allocation structures? Or what are the data structures which we could use to maintain this allocation tracking mechanism? Any clues? Any thoughts? Well, some of you might be thinking that one data structure that we could use could be bitmap, right? Bitmap is just a map that stores if every single bit is either free or it's occupied. And we have one bitmap for inodes that could be stored inside the one block that we reserved. We can have another bitmap for data blocks that can be stored for to see where do we have vacancy inside the data block. So if we have here, how many data blocks do we have? If we have 56 data blocks and 5 inode blocks, so we have just 5 entries into this, 2, 3, 4. Well, the shape of the bitmap could be just something like this, 3, 4, 5. So we have 0, 1, 2, 3, 4, 5. And then for the data block, we could have again from 0, 1, 2, 3. I wouldn't be troubling myself to count until all 56 blocks. That means the last block will be 55 because we started from 0. So now what each one of this bit could say us is it could either store 0 or, well, these are just the numbers, but what this bit is actually storing is it could store 0 if it's free, if that bit that I know that index is free, and it could store 1 if it's already allocated. Very simple data structure, but very efficient to manage what, so it gets our purpose done, right? What are another ways? Any other thoughts on what other data structure we could use to track what blocks are free and what blocks are already allocated? We could use something like a free list. What do this free list do is that points to the free blocks. So we can have a list that directly points to the free block. So let's say we can have this, like the first entry into our free list is the first available free inode. In this case, if it's inode 0, then the second entry in our free list could be the second available free inode. That, let's say if it's 2, then we would store that, so on and so forth. In the same way, we would maintain the similar type of free list for data blocks. So whenever we have like a new data coming in, we could just look into the head of the free list. We know that, okay, the block at ID 0 is available. So whatever we want to store in there, it's ready. If it doesn't fit in block at ID 0, and block at ID 0 is already filled, then the free list will be updated to move its head to the next, and then so on and so forth. So a data structure like this also could be maintained to keep our allocation, track of allocations and track of free space that we have on our disk. Any other clues, any other data structures we could use? Well, think of it. and keep thinking. Let's proceed into our discussion. If you can come up with, think of other data structures that you could use, then it's a good idea. You could compare and trade off the benefits of using each of these different data structures. Like, what are the benefits if you use bitmap versus what are the benefits if we use data structure like free list versus what are the benefits if you use that new data structure that you're thinking of right now. And I'm sure you would be able to come to a very well thought design decision with such a thought process of measuring your trade-offs of pros and cons. Now, let's say that we continue with our idea of maintaining a bitmap into our allocation structure, into the file system that we are designing. Why I would choose a bitmap is it's very simple and it's very easy. We would exactly know, depending on the content stored inside the bitmap, whether that block is free or not. So very simple to maintain. But what are the cons of such a bitmap? Did anybody think of that? If you're with me in this lecture, then well, you would already be thinking that does it actually make sense to give an entire block that is of 4 kilobytes to just store a bitmap about inodes? And we know that in this, we are using number of inodes, maximum number of inodes that we could have is 80 inodes. So we would be using this entire block of 4 kilobytes just to store this 80 inodes. And we also know that inodes are not like a huge data structure, so a huge struct. So they do not occupy much space. On an average, they occupy space between 128 to 256 bytes. So, well, you are on the right track in thinking of different trade-offs if you have already thought of this. It does not make sense because it's a lot of space wastage. But initially, to keep things simple, first our goal is let me design something and then I would worry about making it more efficient, right? So let's just stick to it that, okay, in order to keep things simple, we have this whole block that we give to store a bitmap about inodes, and we have another whole block that we use to store the bitmap about the data blocks, which data blocks are free. So now, how many do we have any blocks left in our file system? Well, note that we still have one block empty, right? We didn't leave that one block for nothing. So what do we store in that single block? So we started filling from the back where we kept 56 block reserved for the data, then 5 blocks reserved for inodes, then there's 2 blocks reserved for allocation structures. I'll just acronym that as AS. And still we have this one block left. What do we store in this one block? Didn't we store almost everything that we need? We know now where to find space for new writes. We know from where to read the data by the data that is given that we can access by using inodes. So what else do we need? Well, how do we know that in this design or in this file system that we are designing, how many blocks are reserved towards allocation structures? How do we know from where the blocks that stores the inodes would start versus how many blocks do we have reserved for inodes? How do we know from where my data block starts? somewhere we should store all this critical information, right? Because without those information, we would be paralyzed. We would just have this nice structure of storing allocation structures, inodes, data blocks, but eventually we wouldn't know that, okay, how many of these blocks are allocation structures? So we could read or access a block that's actually storing inode, and we could think it's still allocation structures. It would be a big blunder, right? We don't want to do that. So a block that stores information, or that stores this critical information about the whole logic of how this file system was designed, including information such as any particular information that is related to this particular file system. That could include, for example, things like how many inodes. So here we know that we can store 80 inodes. How many data blocks? So we know that we have 56 blocks. So here, how many inodes, as well as that we could calculate from number of blocks that's reserved for inodes. So we know that, we also know that we have 5 blocks reserved for inodes. We have 56 blocks reserved for data. And also things like where inode data table begins. In our sweet little file system until now, our inode data table begins from block 3. And so on and so forth. So basically, any information that gives you a hint about where we are storing what inside this file system that we are designing. So it's a metadata about the metadata, right? Things like that. Or metadata of where the metadata is itself stored, where the data is itself stored, things like that. This information, because this information is very critical, let's call it super block. So that one last block that was remaining, we call that as super block, and we can store all this information inside that. Now, every file system will have its own super block, its own unique super block, because every file system has some logic behind how it's organizing its data, right? Like even a very simple file system that we are designing here has its own logic. So if we need some data for such a very simple file system, definitely other more advanced file system would also need some data like this. And while mounting these file system, operating system will read superblock to initialize various parameters. And then attach the volume to the file system tree. So as we know that our directory hierarchy begins with the root directory, and in the process of making the file system, first we use mkfs command like that to make the file system whichever we are desiring to use, and then once we make this file system over a particular device or a device partition, such as /dev/NVMe 0 and 1, something like that, then we would have to mount this file system onto one of the operating systems directory. And that wherever we mount that, that would be then the root for this file system. So when we do that mount operation into when we give that mount command, irrespective of which operating system are we using, the similar process of making the file system and then mounting it needs to be followed. In that command of while, like what is actually done underneath that mount command is it would fetch the super block to initialize the parameters that are critical to understand, okay, so now I have, which file system do we have? Let's say we have this very simple file system, VSFS. That information is stored inside the super block with some mystery number. And as soon as an operating system sees that number, it recognizes, okay, this is a very simple file system. And then it has information like, in this very simple file system, we have first, like the 2 blocks that are reserved towards the allocation structures, another 5 blocks that are reserved for inodes, and then remaining blocks that are reserved for the data, things like this. So super block, very, very important. That's the third important metadata structure. Are we done by using all the blocks that we had on our sweet little 256 kilobyte disk? Yes, right? We have used all the 8 metadata blocks, and definitely we would, depending on how the user reads and writes come, then we would start using our data blocks towards that. But we have an idea of what do we want to store in how many blocks. So now that we have this idea of what contents we would need with metadata, under metadata, and how would we organize things and into our file system. Next, let's move on to how we would organize the files. The file organization